I am Ijaz Ahmed. In this lecture, we shall discuss about cycles and permutations, and cycles in symmetry groups and disjoint permutations in symmetry groups. So we start by definition of a cycle. Definition: cycles in SN. Cycles in SN. So let's choose the set X with n elements. Let X is equal to x1, x2, xn be a set with n elements, and let I1, I2, so on, IR be the elements of X, and let alpha be a permutation in Sn such that, so we choose a special kind of permutation which goes like this, such that alpha of I1 is equal to I2, alpha of I2 is equal to I3, so on, alpha of I r minus 1 is equal to IR, and alpha of IR is equal to I1. So we have a kind of a permutation that sends I1 to I2, it sends I2 to I3, and so on. It sends IR minus 1 to IR to I1, and fixes all other elements of X. And fixes all other elements of X. So alpha is a kind of permutation that moves these I1, I2, IR by this nature, and all the other elements of X are fixed by this permutation alpha. Then this kind of permutation is known as a cycle. So actually this has a nice notation in this permutation groups. We can write this alpha is equal to, so actually in a two-row notation, this I1 goes to I2, I2 goes to I3, I3 has the image I4, and so on. IR minus 1 has the image IR, and IR has the image I1. Now this also can be written as a single row notation. It is I1, then I2, then I3, then so on, then IR. And this means that I1 goes to I2, I2 goes to I3, I3 goes to I4, and so on. And this last symbol IR goes to I1. So this kind of a permutation is known as cycle. Actually, this cycle can also have a circular representation. This can also be represented on a circle. So let's construct a circle here. Then here we can write I1. Then this I1 goes to I2. Actually, this is usually written in the anti-clockwise direction. Then I2 goes to I3. So the image of I2 is I3, and similarly the image of I3 is I4, and so on. And here we have similarly IR, and this IR is the image of IR minus 1, and so on. So therefore, under the cyclic representation of this cycle, I1 goes to I2, I2 goes to I3, I3 goes to I4, and so on. IR minus 1 goes to IR goes to I1, and then the cycle repeats. So this kind of permutations are known as cycles. Now we take some examples of the symmetry groups. Let's define the symmetry group S1. S1 is a symmetry group of order 1, so it has only one element, that is the identity element. So this is our symmetry group of the smallest order. Then S2, as we know that the order of the symmetry groups Sn is n factorial, therefore S2 has order equal to 2. So it will contain two elements, one is 1 and another element is 1, 2. So here actually the underlying set that we are choosing here is a set containing two elements 1 and 2. So this S2 is a permutation group that contains two elements. One is the identity mapping, which we shall denote by 1, and another is the cycle of this nature, 1 goes to 2 and 2 goes to 1. So it will contain only these two elements. Now similarly, S3 is a permutation group with 6 elements, because 3 factorial is equal to 6. So it will contain 6 permutations. One is identity mapping. Next we can write 1, 2, 1 goes to 2 and 2 goes to 1, and 3 remains fixed. 3 goes to 3. Now similarly here, next permutation, 1 goes to 3, 3 goes to 1 and 2 remains fixed. Now another 1 remains fixed and 2 goes to 3, 3 goes to 2. This is also a bijection. Now here another permutation is 1, 2, 3, that is it has a cycle representation, 1 goes to 2, 2 goes to 3 and 3 goes to 1, and the last element is 1, 3, 2. So these are the 6 elements of this symmetry group S3. So these were certain examples of the symmetry groups. Now we shall proceed towards one more definition, that is disjoint permutations. So here we have this definition, disjoint permutations. Disjoint permutations. So how do we define these disjoint permutations? Two permutations, alpha and beta, belonging to Sn are disjoint if whenever whenever alpha I is not equal to I, then beta I is equal to I. That means whenever alpha moves I, then beta fixes I, and whenever whenever beta of j is not equal to j, then alpha of j is equal to j. So we call two permutations alpha and beta to be disjoint if whenever one of the permutations moves a symbol, then another permutation fixes it. And similarly, whenever beta moves j, then alpha fixes j. So these types of permutations are known as disjoint permutations. For example, if we choose alpha is equal to 1, 2, 1, 2, 3, 4, belonging to S4. So here under this permutation, 1 goes to 2 and 2 goes to 1, 3 remains fixed and 4 remains fixed. So this is our choice alpha from S4. And similarly, we choose beta from S4 as, that is fixed 1, fixed 2, then this 3, 4. So this is also an element of S4. Now here we can see that alpha moves 1 but beta fixes 1. Alpha moves 2, beta fixes 2. Similarly, beta moves 3 but alpha fixes 3, beta moves 4 and alpha fixes 4. So these kinds of permutations are known as disjoint permutations. Now in this permutation or symmetry group theory, whenever an element is fixed by a permutation, it is usually sequable in writing. So actually we can write also this alpha is equal to 1, 2 belonging to S4. As 3 and 4 are not appearing here, we mean that 3 is fixed by alpha and 4 is fixed by alpha. Similarly, we can write beta as 3, 4. This is an element of S4, so actually 1 and 3 are not appearing here. It means that beta fixes 1 and beta also fixes 2. So therefore these two permutations 1, 2 and 3, 4, these are two disjoint permutations in S4. Now we proceed towards a theorem on disjoint permutations. It states that disjoint permutations alpha and beta belonging to Sn commute. So actually what we need to prove here is that if we have two disjoint permutations alpha and beta, then alpha beta will be equal to beta alpha. So let's proceed towards the proof. What we need to prove? To prove alpha beta of I is equal to beta alpha I for all 1 less or equal to I less or equal to n. So actually the underlying set X that we are choosing here is the set of n elements containing the first n natural numbers. So in order to prove that alpha and beta are commuting, we have to prove that alpha beta I is equal to beta alpha I, where I is some arbitrary symbol from the set X. So here we note that our two permutations alpha and beta are disjoint. So whenever one of the permutations moves a symbol, the another permutation must fix that. So let's assume that assume first that beta moves I. Beta moves I. That is, let beta of I is equal to j, and this j is not equal to I. So first we shall assume that beta moves I. Then actually we have beta of I is equal to j and j is not equal to I. Then beta also moves j. So we are just assuming that beta moves I and I is not equal to j. Then under this construction beta must also move j. For otherwise, what happens otherwise? Otherwise, if beta of j is equal to j, that means if beta does not move j, then beta of j is equal to j, then beta is not an injection. Beta is not injective. Then beta is not injective because what happens then? Because we already have beta of I is equal to j and j is not equal to I. So actually what happens here, that if beta does not move j, then beta of j is equal to j, but we already have beta of I is equal to j, and these two numbers I and j are two distinct numbers. That means if beta of j is equal to j, then beta sends I to j and beta also sends j to j. That means under beta two different elements have the same image. So this means that beta is not an injective mapping, but since we already know that beta is a bijection, therefore it must be injective as well as surjective. Therefore the only thing that we can conclude here is that whenever beta moves I and beta of I is equal to j, then beta must also move j. Okay, now let's proceed towards what alpha does to this I and j. Now since alpha and beta are disjoint, permutations, and beta moves I and j, thus alpha must fix both I and j. That is, we have alpha of I is equal to I and alpha of j is equal to j. Now let's proceed towards calculating alpha beta of I and beta alpha of I. So now we have, therefore, we have alpha beta of I is equal to, now since these alpha and beta are the two elements of Sn, and Sn is the set of permutations, that is the bijective mappings, and this alpha beta I means that we have to calculate the image of I under the composition of two mappings alpha beta. So this is actually also in the form, this can be written as alpha or beta I, and by definition of the composition of function, this is alpha beta of I. Now beta of I is defined to be equal to j, so this is equal to alpha of j, but alpha of j is equal to j. So this means that alpha beta of I is equal to j. Similarly, what about beta alpha of I? So this is equal to beta composition of alpha of I. So this is by definition beta alpha of I. Now as alpha of I is equal to I, so this is beta of I, and therefore this is equal to j. So therefore in both the cases we have alpha beta of I is equal to j and beta of alpha of I is equal to j. So this means that alpha beta of I is equal to beta alpha of I for all 1 less or equal to I less or equal to n. So therefore alpha and beta commute when beta fixes I. We are assumed here that beta moves I, therefore when beta moves I, then alpha beta I is equal to beta alpha I. A similar conclusion follows. A similar conclusion follows. A similar conclusion follows when beta alpha moves I. So in the first step we are assumed that beta moves I. Now when we assume that alpha moves I, then a similar conclusion follows, and we will similarly obtain that alpha beta I will be equal to beta alpha I. And lastly, if both alpha and beta fix I, then alpha beta I will be equal to I and beta alpha I will also be equal to I. Therefore, in all cases, we have that alpha beta is equal to beta alpha. So therefore, we conclude that two disjoint permutations always commute. Now we shall proceed further. So therefore, the conclusion is thus alpha beta is equal to beta alpha whenever alpha and beta are disjoint. Now we make one more definition here. Definition: transposition. Transposition. Transposition is a cycle of the form, a cycle of the form, a comma, sorry, a cycle of the form AB is called a transposition. So a cycle of the form where A goes to B and B goes to A and everything other remains fixed, then this kind of cycle is known as a transposition, or this kind of permutation is known as a transposition. So actually we also need one more definition: length of a cycle. Length of a cycle. If alpha is equal to, suppose I1, I2, I3, so on, IR is a cycle, then R is known as a length. R is called the length of the cycle. Length of this cycle. And also in this case, alpha is also known as an R cycle. So R cycle means a cycle of length R. Therefore, in this notation, in this definition, we can call a transposition is a cycle of length 2. So therefore, thus a transposition is a cycle of length 2. So a cycle of length 2 is known as a transposition. Now we have one nice result here. Every cycle, every R cycle, every R cycle can be written as the product of R minus 1 transpositions. So whenever we have a cycle of length R, then that cycle of length R can also always be written as the product of R minus 1 transpositions. The solution is actually very easy here. So let alpha be an R cycle. So let alpha is equal to I1, I2, I3, so on, IR be an R cycle. Then we can write, then we have like this. Then I1, IR. Let's choose this to be the first transposition. Then second is I1, IR minus 1. Then I1, IR minus 2, and so on. And similarly, I1, I3, then I1, I2. So this kind of a product, when we look at the image of, when we take the product of all these permutations, we will obtain this R cycle alpha. So actually, let's try to compute the images of these elements. Now we can see here that I1 goes to I2. Now here I2 remains fixed. So therefore, there is no I2 appearing here in these permutations. Therefore, finally, under this product, I1 goes to I2. Now, let's try to evaluate the image of I2. Now here I2 goes to I2 goes to I1, and here I1 goes to I3, and I3 will not be appearing here. Therefore, I2 goes to I3. So therefore, we can easily check that the product of these R transpositions is the cycle alpha, is the R cycle alpha. So this is actually the notation for this R cycle alpha as a product of R minus 1 transpositions. For example, if alpha is equal to 1, 2, 3, 4, then we can write alpha is equal to 1, 4 into 1, 3 into 1, 2. Similarly, if some beta is a cycle, which is 1, 3, 4, 2, then beta can be written as a product of three transpositions, that is, it is equal to 1, 2 into 1, 4 into 1, 3. So with these examples, we conclude this lecture here.